Good morning students. Today we discuss about partial differentiation. The process of differentiating a function of several variables with respect to one of its variable while keeping the other variable fixed is called partial differentiation, and the resulting derivative is called a partial derivative of the function. Now, formal definition of partial derivative of a function of two variables. Let f d to R, where D is an open subset of R2, that means R cross R. If limit delta x tends to 0, f of x plus delta x comma y minus f of x comma y divided by delta x exceeds, there we say that the partial derivative of f with respect to x exists, and it is denoted by fx x comma y. Similarly, limit delta y tends to 0, f of x comma y plus delta y minus f of x comma y divided by delta y exists. There we say that the partial derivative of f with respect to y exists, and this is denoted by f y bracket x comma y. Hence, if z is a function of x comma y, that is, if z is equal to f of x comma y, then fx x comma y is equal to limit delta x tends to 0, f of x plus delta x comma y minus f of x comma y divided by delta x, and fy x comma y is equal to limit delta y tends to 0, f of x comma y plus delta y minus f of x comma y divided by delta y, provided the limits are exist. So we see that if z is equal to f of x comma y, partial derivative with respect to x, we treat y as constant while differentiating the function f with respect to x. Similarly, when partial derivative with respect to y is obtained by treating x as constant, that we differentiate with respect to y. Now, if z is equal to f of x comma y, then partial derivatives fx and fy are also denoted by the symbols del f by del x, del z by del x, or zx, or dx of f, and fy can be written as del f by del y, del z by del y, zy, or dy of f. And the values of partial derivative of f of x comma y at the point x0 comma y0 are denoted by del f by del x at the point x0 comma y0 is equal to what? fx x0 comma y0, and del f by del y at the point x0 comma y0 equal to fy x0 comma y0. Now we discuss examples. First, example number 1. If f of x comma y is equal to xy square ln x plus y, find f of x, fx and fy. So first we have to find what? fx, that is the derivative of the function of the given function xy square ln x plus y with respect to x, where we treat y as a constant. So first, fx x comma y, here the function is xy square ln x plus y, so we consider y as a constant. So first y square out of the bracket, y square, then we have to derive x ln x plus y. First function is x So we write x as unchanged. Now derivative of ln x plus y with respect to x. So this will be 1 by x plus y. Now derivative x derivative of x is 1 and y as constant, so the derivative of y is 0 plus. Now second function unchanged, ln x plus y, and the first function is x, so the derivative of first function is 1. Now bracket closed. If we arrange this, is equal to y square x by x plus y plus ln x plus y. And similarly, we have to find now f of fy. Fy means what? Derivative of the given function with respect to y, treating x as a constant. So fy x comma y is equal to x constant, and we have to derive y square ln x plus y. First function is y square unchanged. Second function derivative 1 by x plus y. Now bracket x derivative of x is 0 as constant plus derivative of y is 1, bracket close, plus second function unchanged ln x plus y. Now derivative of y square is 2y. Now bracket close, and we arrange it is equal to x bracket open y square by x plus y plus 2y ln x plus y. Now example number 2. Find fx 1 comma 2, that is the derivative with respect to x at the point 1 comma 2, and fy 1 comma 2 for the function f of x comma y is equal to root over x to the power 4 plus y to the power 4 plus 1. So this function is of two variables x and y. First we have to find fx x comma y, and fx x comma y is equal to what? Derivative of this function. So derivative of the function is what? 1 by 2 root over x to the power 4 plus y to the power 4 plus 1 and into 4x cube. We arrange it 2x cube by root over x to the power 4 plus y to the power 4 plus 1, and fy x comma y is equal to what? 1 by 2 root over x to the power 4 plus y to the power 4 plus 1 into 4y cube is equal to 2y cube by root over x to the power 4 plus y to the power 4 plus 1. Now at that point 1 comma 2, we just put the point 1 comma 2. So fx 1 comma 2 is equal to 2 into 1 cube divided by root over 1 to the power 4 plus root to the power 4 plus 1, which is equal to 2 by root over 18 is equal to root 2 by 3, and fy 1 comma 2 is equal to 2 into 2 cube by root over 1 to the power 4 plus 2 to the power 4 plus 1, which is equal to 16 by root over 18 is equal to 8 root 2 by 3. Now example number 4. So that fx 0 0 is equal to 0 but fy 0 0 does not exist, where f of x comma y is equal to x square plus y sine of 1 by x square plus y square when x comma y not equal to 0 0 and 0 when x comma y is equal to 0 0. This problem we will solve by definition. We know our definition. Fx x comma y is equal to what? Limit delta x tends to 0 f of x plus delta x comma y minus f of x comma y divided by delta x. We apply this definition. Now solution, we have fx 0 0. Here the point is 0 0. That means the value of x here is 0 and the value of y is here 0. So fx 0 0 is equal to limit delta x tends to 0 f of delta x comma 0 minus f of 0 0 divided by delta x. Putting this value in our function, so we can write limit delta x tends to 0 delta x whole square sine 1 by delta x whole square minus 0 divided by delta x is equal to limit delta x tends to 0 delta x sine 1 by delta x whole square. So putting the limiting value, we get 0 is equal to 0. Now fy 0 comma 0. From definition we know that fy x comma y is equal to limit delta y tends to 0 f of x comma y plus delta y minus f of x comma y divided by delta y. So we apply this definition. Here the value of x is 0 and y is also 0. So the point is 0 0. So fy 0 0 is equal to limit delta y tends to 0 f of 0 comma delta y minus f of 0 0 divided by delta y is equal to limit delta y tends to 0 delta y sine 1 by delta y whole square divided by delta y. Cancelling delta y, limit delta y tends to 0 sine 1 by delta y whole square, which does not exist because we know minus 1 less than is equal to sine 1 by delta y whole square less than is equal to 1. So here we prove that fx 0 0 is equal to 0 but fy 0 0 does not exist. Now partial derivatives of a function of three variables. In same way we can apply partial derivatives for three variables. For three variables, fx is equal to limit delta x tends to 0 f of x plus delta x comma y comma z minus f of x comma y comma z divided by delta x. Similarly for fy, limit delta y tends to 0 f of x comma y plus delta y comma z minus f of x comma y comma z divided by delta y. And for the variable z, fz is equal to limit delta z tends to 0 f of x comma y comma z plus delta z minus f of x comma y comma z divided by delta z, provided all these are exists.